Good day, I'm Norman Wildberger. With today's video, we move towards gazing at modern set theory, which is unfortunately fraught with difficulties, logical and conceptual problems. This is a little bit of a painful thing for me to have to do because I'm going to have to say a lot of negative things. I'm seriously unimpressed with modern set theory and the approach of modern mathematics towards it. Basically, I feel that most modern mathematicians are deliberately not gazing over there in the corner, addressing the very serious, essentially obvious problems with the subject. Okay, so the kinds of problems that we're going to be looking at vary quite considerably, but really the starting point is with the question, what exactly is a set? It's important to realize that this very common question of, do infinite sets exist or not, yes or no, this is really only one aspect of the question. In fact, not necessarily the most fundamental aspect either. The question about what actually the word set means is actually the fundamental question. It's the fundamental problem in the subject. One of the difficulties is that the word set is a common word in the English language, and almost everybody has some kind of intuitive idea because it's a word that's used out there in the real world. In the real world, we find definitions of the word set. For example, Merriam-Webster gives the definition, or one of the definitions of set, to be a number of things of the same kind that belong or are used together. The Cambridge Dictionary, we see that a set is a group of things that belong together. The Oxford Dictionary, a group or collection of things that belong together or resemble one another or are usually found together. And there's a coherence there. Well, we're definitely getting a pretty good idea, at least for ordinary usage in the real world. Another very instructive thing to look up is the thesaurus. And this actually is quite interesting for us. So the thesaurus gives us a whole bunch of near synonyms to the word set, other words which are interchangeable with set under certain conditions, including collection, group, arrangement, clump, multitude, batch, cluster, formation, body, host, bunch, lineup, bundle, lot, display, menagerie, throng, assortment, compendium, aggregate, ensemble, assemblage, class, clique, progression, and no doubt you can think of some more yourselves. So one way of trying to explain to a young person what a set is to use some of these other words. So a set of birds is like a group of birds, or a bunch of birds, or a multitude of birds. So we can use some of these words to describe what other words mean. And there is a problem of potential circularity here. So, we could fall into the trap of saying, well, a set is a group. And then if somebody asks us what a group is, we say, well, a group is a collection. And what's a collection? A collection is a menagerie. And eventually we get back to where we started. So there's definitely a little bit of a danger there. But nevertheless, it's interesting to realize that this is a very common meaning in English, as evidenced by the fact that we have a lot of synonyms for this word. So that's all well and good in ordinary life. We want to take this word and apply it to mathematics. Thereby, we need to actually make it much more precise. We need to clarify what does it mean in a mathematical sense. This turns out not to be so easy at all. All right, so let's move toward the idea of trying to establish or investigate whether or not we could actually give a precise meaning to this word set in the mathematical context. Okay, so we're not going to assume that we already have such a definition. Very important to make this point. Okay, so we do not have a definition yet. We're looking to see whether it's possible to create such a definition. And maybe it is, and maybe it isn't. Okay, but in any case, there are certain kinds of sets that we certainly want to end up being included in our definition. For example, these kinds of sets. A, the set 1, 2, 3. And this is the usual notation that we would like to introduce, some sort of curly brackets, and the elements or the objects or the things inside the set separated by commas. And with this important convention that the actual order of the objects doesn't matter. We can interchange the order and it's still the same set. So the set 1, 2, 3 is the same as the set 2, 1, 3, which is the same as the set 3, 1, 2, and so on. Here's a set B with a single element. The element is a number, the number 47. Here's a set C, which is a little bit more complicated. It has 3 objects in it, as you can tell by the fact that there are these 2 commas. So this is one element, this is another element, and this is another element. But this element here is itself a set consisting of 2 numbers. This one here is also a set consisting of 1 number, and this is not a set, just a single number. So probably we do ultimately want to be able to consider things like this and call them sets. So we want sets to be objects which can be included as elements of other sets. So I've said that we want a set to be unordered. Doesn't matter if we permute the entries. But we only want one of any given element. We do not want to allow multiple copies of the same element in a set. So for example, this thing, D equals the set 1, 3, 1, 2, is officially not a set because there are 2 1s. Okay, so that's sort of the idea that we want sets to have distinct elements. It turns out to be actually useful. We will talk about objects like this. They are more usually called multisets, kind of an extension of the idea of a set. Very important actually in applications. But the set notion proper is going to exclude this possibility. So if we see something like this written down, we'll say, no, no, that is not a set. Informally, something else that we want is that the objects in the set, in other words, the elements of the set, should be well-defined mathematical objects. So closely related to the question of what is a set is the question, what do we mean by a mathematical object? For example, are any of the following sets? So here's a set F, which consists of Fred. Okay, Fred is an English word, usually referring to the name of a person. There are many people called Fred. Does this make sense? Is this a legitimate set? Well, maybe it is in certain contexts, like in ordinary life. You know, might have a committee and the committee has one person on it, and that's Fred, and okay, so Fred is constituting a set in this case. But do we want this kind of thing to be a mathematical set? That's a question. How about something like this? G equals 1/2 plus 1/3. Okay, this is a mathematical thing, but what kind of thing it actually is a good question. It's an arithmetical expression involving rational numbers with an operation, and we can certainly evaluate that to a rational number, especially if we know a little bit of rational number arithmetic, namely 5/6. So this thing evaluates to 5/6, but are we allowed to write just this expression, or do we really need to write 5/6? It's kind of a question about what kind of mathematical objects we're going to be allowing. For example, this thing here, the set consisting of 2 to the 3, where the 3 exponent is written on the left. Now for most of us, we look at this and say, well, it looks kind of mathematical, but what does that mean? If it was 2 to the 3, we would know what that means, but this thing here is unfamiliar, even though it looks kind of mathematical. So are we going to allow something like this that sort of looks mathematical, but maybe doesn't have a pre-existing mathematical meaning? Another question is, are we going to consider sets with an infinite number of elements? Of course, this is a very fundamental question. Are we going to restrict ourselves to things that we can write down completely? Or are we going to allow 3 dots? Are we going to say that the set X consisting of 1/1, comma 1/2, comma 1/3, comma 1/4, dot, 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 is a legitimate set? There's clearly some potential debate about that. So here's another example, something that's potentially ambiguous. The set of all possible equations. It's kind of ambiguous. We don't really know exactly the realm of what an equation is. Equation could refer to all kinds of different things. And all possible equations, well, you know, that's a huge thing. Is it going to be a legitimate object of our mathematical theories? It's a question. We've had quite a lot of experience in introducing different kinds of mathematical objects, and we've seen that invariably we have to address the question of when two mathematical objects are the same. When are two integers the same? When are two rational numbers the same? When are two polynomials the same, etc. So the same story is going to apply here to our set theory. Whatever a set turns out to be, we are going to want to ask the question, how do we tell if two sets A and B are equal? What is the definition of equality of sets? And how do we actually tell whether two sets are equal? So for example, here are two relatively small sets, A and B, and you can see the elements. There's some numbers and a few letters as well. We might ask, is A equal to B? And you can see that it's not so easy to answer this question. Especially if these lists were considerably longer, it would be very challenging to answer this kind of question. Because of the unordered aspect of the set makes it very challenging. We basically have to order the sets, if they're long sets, in order to be able to answer this kind of question. So computationally, this is a very knotty problem. But there's another sort of aspect of this question. How can we tell if two mathematical objects which are inside the sets are themselves the same? So in order to be able to tell that these two sets are the same, we'd have to say, oh, this is a 21 here, and oh, there's a 21 here, and these two 21s are the same. So in this case, they're evidently the same. But what if we're representing this 21 in a different fashion from this 21? We have to be able to recognize that this mathematical object and this mathematical object are either the same or not the same in order to be able to tell that the sets are the same and not the same. So we have to have mastered equality for all the mathematical objects that we're going to be considering in our set theory in order to talk meaningfully about the equality of sets. For example, the set C. Set C is 3 times 7, and then the smallest prime greater than 18, and then 17 equals 13. That looks like an equation. Okay, is an equation allowed to be an element of a set? Well, maybe. Okay, here's another set consisting of 19, and another equation, 13 equals 17, and another arithmetical expression, 22 minus 1. So we can ask, are these two sets the same? And you'll probably see that we probably want them to be the same because 3 times 7 is the same as 22 minus 1, and the smallest prime bigger than 18 is in fact 19. And this equation is, I suppose, pretty well the same, I suppose, as this equation. But clearly, to make that very precise, we need to have a notion before that of when two equations are the same, of whether we're going to allow this representation of the number to be the same as this representation of a number, and what kinds of arithmetical expressions we're going to be allowing inside our sets. You can imagine this sort of from the point of view of a computer scientist who's trying to create a mathematical program that deals effectively with sets. And if we're going to allow arithmetical expressions as elements of sets, or statements like this, or equations, that programmer is going to have prior sort of subroutines that deal with all those kinds of objects and deals with all the kinds of potential inequalities or equalities involved with the various types of mathematical objects that they're considering. You know, it's a sort of massive programming problem, I suppose, if we want our sets to be very general kinds of mathematical objects. And how are we going to deal with sets whose elements cannot be specified but only described? So, for example, consider this set E, which has 3 elements. The first one is the smallest prime bigger than 20 to the 20 to the 20 to the 20 to the 20. The next element is the smallest equation that will never be written down. And the third element is the set of all sets with exactly one element. So is this a legitimate set? We have to ponder, what are these things? I mean, the smallest prime bigger than this number. It's the same kind of question as the smallest prime bigger than 18. But we can all figure out what the smallest prime bigger than 18 is. None of us are anywhere close to being able to figure out what the smallest prime bigger than this number is. So far, far beyond our computational abilities. So is this a legitimate thing to write down? Are we really writing down something that makes sense? Are we allowing ourselves to write down descriptions of mathematical objects as opposed to actual specifications of those objects? And this, the smallest equation that will never be written down. Okay, sounds a little bit sort of circularly difficult. Okay, there's all kinds of equations. Some of them will never be written down. Okay, then of all the equations that can never be written down, there's the smallest one, maybe. And so that's the one we're talking about. All right, so by definition, we can't write it down, but we want to include it in the set. You know, are we going to allow ourselves that? And this is the set of all sets with exactly one element. Okay, so there are sets with one element. There are many sets with just one element. And how about the set of all sets with one element? Is that a legitimate mathematical object? We can certainly never write it down, but we can sort of describe it in this loose kind of way. Is that allowed? What about self-referential sets? So suppose I say that, let's consider the set F, which is equal to the set F. Is this a legitimate kind of thing? So if I replace this F with what it is, namely F is equals the set F, then I write F equals the set of the set F. And then I can replace this F with the same thing, and I find that F equals the set of the set of the set F. How about taking the limit, as we like to do in modern mathematics, right? We like to take the limits. We like to go to infinity. So why don't we just go to infinity? We carry on this process to infinity, and we get this kind of expression for F. It's a bracket, another bracket inside, another bracket inside, another bracket inside, and a whole bunch of dots. Does this make sense? Is this a legitimate usage of 3 dots? Well, I know you all know what I think about such things, but what do you think? Another natural question is, should we allow a set with 0 elements? Are we going to include the idea of a set like G, which is just a pair of brackets with nothing inside? So I remind you that the number 0 hasn't been around that long. The ancient Greeks didn't have 0. It's basically Hindu-Arabic introduction around 500 AD in India. And so there's something a little bit sophisticated about the idea of 0. And so there's something a little bit sophisticated about the idea of a set with 0 elements. Does that really count? It's a question. I know most of us are quite used to this, but perhaps it does take some getting used to. And it's not entirely clear that it should be the case that empty sets are included. Along the same lines, and a little bit more exploratory, how about sets with a negative number of elements? You could argue, well, if you can allow 0 elements, why not include -1 elements? So here's how we take the union of sets. The union of set 1, 2 with the set 3 is set 1, 2, 3. How about the union of the set 1, 2 with the set consisting of -1 2's? So following a counting practice, let's write a negative number of 2's as a bracket with the 2. So this means not -2, but means there's a 2 there, but there's a negative number of 2's. Does that mean anything? And if so, is it the case that if we take the union of these two, that the 2's somehow perhaps cancel? Okay, this is very questionable, but one might imagine that some beginners in set theory might think, well, maybe we could have such a theory. If we take Fred union sort of anti-Fred, do we get the empty set? I don't know. At least it's possible, right? It might be consistent for somebody to create such a set theory, and they would then say, yeah, my set theory is better than yours because I include sets with -1 elements, not just 0 or positive elements. Okay, now we come to a much more serious issue, okay, which is highly problematic when it comes to thinking about infinite sets. This question about choice versus algorithmic constructions of sets. So the same kinds of issues that we encounter dealing with infinite decimals, with Dedekind cuts and Cauchy sequences, raise their heads here in the set theoretical world. Are we allowed to create a set by making an infinite number of choices? For example, let me do that for you here, okay? I'm going to create a set C. It's going to be an infinite set. And the first element is going to be 19. And the next element is going to be 20. And then maybe I'll choose minus 131. And then I might choose 51 over 49. And then I just have to make sure that I do something that's different from what I've done before. Maybe I'll add, hey, I'll add a triangle. That sounds cool. And now I'm going to add the letter R. And now I'm going to add the letter, maybe T. And now how about 13 squared? And I'm going to keep going. There's 3 dots there. Okay? That 3 dots, of course, represents that I'm going to carry on making choices past the end of the month, past the end of the decade, past the edge of time. I'm going to carry on to infinity, making choices, keeping on adding more and more stuff to infinity. Is that a legitimate mathematical object? The set C that Wildberger creates. As opposed to that, there's sort of an algorithmic approach to a set. So I'm going to create another set using an algorithm. So here's the algorithm. So the algorithm step 1 is insert a 1. Okay, I've inserted 1. And step 2 is insert what you've built so far and repeat. Okay, so what I built so far is a set with just 1 element. So I'm going to insert that set that I've created so far, which is, that's what I've created so far, right? I'm inserting that. Okay, and then I'm going to repeat this. So now I'm going to look to see what I have. I now have a set with 2 elements. I'm going to insert that set into what I already have. Okay, so that was the set 1 and the set 1. Okay, I've just inserted that. And now at the next step, I'm going to insert what I already have, which is a set consisting of a 1, the set 1, the set 1, the set 1. Well, I guess I have to end it there. Okay, the brain's starting to hurt if I have to do this too often, but it's reasonably coherent instruction. The computer could go on and keep on adding more and more elements, and we could carry on this way. So this is a construction of an infinite set, if you believe such things. And this is a construction of an infinite set, if you believe such things. And a natural question is, well, if you are going to believe in this religion, this theory of infinite sets, are you going to think about sets as being defined in terms of choice? Or are you going to think in terms of sets defined as algorithms? Or are you going to mix and match? Allow occasionally these kinds and occasionally these kinds. Okay. So whenever you're dealing with infinite processes, this question of choice versus algorithm is never far away. You can try to avoid it and not think about it, but the question is still there. Are you thinking about this kind of infinite process or this kind of infinite process? And there's a big difference, as we've already seen with our discussion with real numbers, between these two ways of thinking about things. The theory of sets is quite different if you think about them this way or if you think about them this way. They're very, very different theories. So which one do you want? There's another aspect of this choice versus algorithm kind of dichotomy that I also want to draw to your attention. That we can ask the same kinds of questions with regard to nesting rather than listing. So instead of thinking about a set as being a listing of things, we can also think in terms of nesting. So let me give you an example. So here's a set R. Okay? It's the set consisting of A and B. Have I defined a set with this? Well, it probably depends on what A and B are. If A and B are variables, and you know what a variable is, then perhaps you could say, yes, the set R is complete as it stands. But if I tell you that A and B are not variables, but they are in fact sets, then you probably have a right to ask, well, what are they? Let me tell you what they are. So A is the set C, D. And B happens to be the set E, F. And what are C, D, E, and F? Well, suppose that I tell you that they also are sets. So now you can see that in order to define R, not only do I need to define what A and B are, I've done that there, but now I'm furthermore obliged to tell you what C, D, E, and F are. So maybe I could go and do that. I could say, all right, C equals, say, X, Y, Z, and D equals F, and E equals 1, 2, R, and F equals, what letters haven't we used yet? K, L, M. And you can see that I can kind of keep on doing this, right? And I could have either a choice point of view or an algorithmic point of view to doing this. You may have thought that there was a pattern when I went from here to here, but from here to here it looks like my pattern is much less clear. Maybe it's the case that I'm just making things up as I go along. That would be like a choice point of view. So at each stage I'm allowed to take the undefined object so far and just create a new definition of what it is in terms of yet more undefined objects. And I can keep going like this to infinity. That would be one point of view. Another point of view would be saying, well, we'd rather prefer an algorithmic approach to this kind of construction. That there's some computer program that actually tells us how to go from one level of this nested bunch of sets to the next level. And finally, another kind of question that we might ask about this sort of fledgling set theory that we're looking towards creating is, are we going to allow sets given by conditions which we can't check or can't easily check? For example, P, the set of n, such that n is an odd perfect number. So a perfect number is a number like 6. If you take the sum of its divisors, 1, 2, and 3, you get 6 itself. So it's called a perfect number. 28 is also a perfect number. So there are perfect numbers known, but they all happen to be even. And it's a famous unsolved problem in number theory about whether there are or are not any odd perfect numbers. So nobody knows. So I can write down this statement, but have I really defined a set or not? Nobody can say whether this is the empty set or whether it has some elements in it, and if it has elements, how many there are. We don't know. So is this a valid kind of set? All right, so we've listed at least some of the issues that we would expect to have to deal with, have to confront, and sort of examine if we're going to create a theory of sets. It's not so easy at all. It's not so straightforward. There's lots of decisions that have to be made, that we're going to accept this and not accept that, and this is okay and that's okay, but we have to have a prior theory of this and that and so on. Okay? Not easy at all. Interestingly, modern set theory started with a very particular individual at a very particular time. This was Georg Cantor, a German mathematician who lived from 1845 to 1918. He was a very courageous and ultimately tragic figure in the history of mathematics, but had a very huge influence on the development of mathematics. So his story is intimately interwoven to this story of set theory. In the 1870s, he clarified this idea of set, which he then went on to develop the set theory. So in German, the word for set is Menge, which actually had been introduced by Bolzano, that term, a few decades earlier. So here's the original German definition of Cantor. Here is the English translation. A set is a gathering together into a whole of definite, distinct objects of our perception or of our thought, which are called elements of the set. If you look back to our first slide, it's not so much different from the colloquial definitions that we find in the various dictionaries these days. Is it sufficient to deal with the various issues and problems that we've suggested are part of the story? Well, I don't think so. And probably Cantor realized this himself, that this definition is just not precise enough to say precisely what a set really is. And this turned out to be a major issue. It turned out that, in fact, yes, this definition was too ambiguous and not precise enough, and it couldn't support a consistent theory. The theory that eventually developed from this basis was ultimately logically flawed because of the weakness of the actual definition. And I hope you can see from the previous discussion in this video why this definition is weak, because it really doesn't address any of the natural issues that even a beginner student might easily ask about this notion. So my opinion is, and I'll sort of lay out my cards on the table here, is that the term set is too general and open-ended to be pinned down with a proper mathematical definition. It's too ambitious to hope to be able to define properly and clearly and carefully the word set in the way that we're trying to do. The term set, like the terms number, function, sequence, statement, formula, this is a meta-mathematical notion. It's a concept coming from the English language or from our ordinary language. This is a meta-mathematical notion from ordinary language, which, although it has a reasonable meaning, rough meaning in ordinary language, when we try to bring it into mathematics, all of these terms just are too broad and their corners and boundaries are too ambiguous to allow us to say clearly what we're talking about. In mathematics, we need to say exactly, clearly, and logically what the fundamental words mean. This is a prime obligation that we have. We cannot avoid it. But all is not lost. Okay? So it turns out that set theory, in fact, is a very rich theory. It's a very rich and fascinating theory, in fact. But to get at it, we need to lower our expectations and restrict our approach. By doing that, we can introduce more limited versions of these concepts in more precise, logical, and constrained settings. So by being less ambitious, we can be more precise. And we can, in fact, create a reasonable kind of introduction to set theory. So what I plan on doing is, instead of immediately critiquing the modern set theory, which is in sore need of critiquing, but I'm going to put that off a little bit, and I'm going to show you a more logical and careful approach to the subject. So we're going to build up the beginnings of a proper theory of sets, albeit in a much more restrictive and precise domain. And then we'll have some good basis for going on and having a look at what actually is out there with the 20th century theory of set theory, which is highly problematic. All right, so I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.